Bismillahir Rahmanir Rahim. Dear students, today we are going to discuss another reaction about the formation of carbon-nitrogen bond, and this is the last reaction of this type of bond reaction in our syllabus. Ugi reaction is basically about the synthesis of amides. During this reaction there is creation of two carbon nitrogen bonds. One nitrogen is attached with two carbons of different moieties. This reaction involves four components for the synthesis of the final product, and these four components include the use of amine and amine, number 1, number 2 aldehyde or ketone, number 3 isocyanate, and number 4 a carboxylic acid. So all of these four components are mixed with each other, and this is one part synthesis, and we get the final product of amides. The main key concepts of today's lecture include introduction to multi-component reaction, the difference between the multi-step reactions and the multi-component reactions, and the importance of multi-component reactions, introduction to UGI reaction, and then finally the overall mechanism of this reaction in aprotic solvent and also in protic solvent. Here we first talk about multi-component reactions. These are the reactions which involve more than two starting compounds, that is 3 starting compounds or 4 starting compounds are made to react together in one pot at the same time. This multi-component reaction, which we abbreviate as MCR, also play an important role in the combinatorial chemistry. Combinatorial chemistry mean combination. You can say this is the technique in which we can get a large number of compounds in a single step, in a simplest process, in a one step process. How is it possible? By using MCR, multi-components, for the reaction, because we know that every reaction has some variable. Let's suppose for this UG reaction, number 1 there was amine, so we can use simple ammonia, primary amine, secondary amine, and in primary amine there are a lot of variation of the R group and so on. Likewise we use carboxylic acid, there are a number of variation, list of carboxylic acids which can be used. Likewise we are using isocyanate, there can be a number of isocyanate. No doubt at the start of this reaction, that is UG reaction, there was no much work on it because of less availability of isocyanate, but now a large number of isocyanates are available in the market, and so this reaction has been used for the synthesis of a large number of compounds, Second, we were using aldehydes and ketones, the fourth one, and so there also a variety can be used in this class of compound. So due to a large number of variation in the structure of these interacting species, the interacting components, we can get a large number of molecules which can be used further for drug discovery program and etc. Similarly, next importance as feature of this MCR reaction is that this simplifies purification. because all the reactants have been used in one step and we have to get the product simple in one step. So there will be it will be easy for us to purify one compound and from this reaction mixture. Otherwise, if there are used a lot of steps, or it involves a number of steps, every step has its purification process, then we have a great loss of products, and you can say there will be a great decrease of the yield. MCRs an attractive synthetic strategy to due to an attractive synthetic strategy due to easy and rapid access to large libraries of organic compound. As we have discussed, due to structural variation, we can get a large number of compounds from this single step reaction. MCR has an importance in the field of drug discovery program, and now the researchers are using this MCR technique for the synthesis of heterocyclic compounds, and we know that heterocyclic compounds have much importance in the drug discovery program, and a lot of drugs involve heterocyclic moieties in them. So therefore researchers are moving towards the synthesis of heterocyclic compound by using this multi-component reaction technique. Isocyanide multi-component reaction methodologies have also applications in most stages of the drug discovery process, spanning lead discovery, lead optimization, and final drug manufacturing. We know that isocyanide is one of the component of this Ugi reaction also, but isocyanide has also been used by a list of other multi-component reactions as a component. So it is not only involved in Ugi reaction. And here the terms used here, one is the in the drug discovery process, spanning lead discovery, lead optimization, and final drug manufacturing. Lead in medicinal chemistry is a term which is used for that molecules which is the basic unit of a natural drug, and then we synthesize a similar type of molecule for the cure of some disease. We know that, for example, we get a naturally occurring molecule which is antimicrobial, or you can say anti-tumor agent, and then we analyze the structure of that species. Then we combine the molecules in such a way that we get a molecule which has close structural resemblance to that naturally occurring compound, and so it may be involved in the cure of the disease. This is because naturally occurring moieties are in too much less amount, and we cannot use in excess due to less availability. But synthetic synthesis can be used for the synthesis of a large amount of a molecule. So therefore it is a multi-component reaction, an important reaction for the drug discovery program. Multi-step reactions can be compared with the multi-component reaction. In multi-component reaction, one part synthesis is involved, but in multi-step reaction there are a large number of steps which are involved for the production of the final product. One part here, one thing should be clear, that in multi-component reaction, that is one part synthesis, does not mean that all the reactants have been added at the same time. It may be like, for example, I give the example of Ugi reaction, which involve an amine, aldehyde, carboxylic acid, and isocyanide. First we combine, we mix together an amine and an aldehyde to get imine. Then we add isocyanate, then we add carboxylic acid along with the isocyanate, both are added at the same time, and then we get the final product. But all this thing is happening in one pot, that is, we have not separated anything by the combination of first two reactants. All are involved in one pot and we get the final product. So first we talk about the multi-step reaction. These are divergent reactions. Divergent mean it is also a technique which is used by the organic chemist to get a large number of compounds. But this large number of compounds in this sense that you can see here as an example, that A or B are combining with each other to form C and D. Then C is broken or decomposed into two compounds F and G. D is treated with E to get the H and I product. So we were combining only two products in first step. Then we get the C and D. C and D are separated from each other. After purification, we move these compounds C and D into the final product, that C is converted into F and G, D is converted into H and I. So the scientists think that a large number of compounds have been synthesized by using two or three compounds. The A or B are two compounds, and then we also involve E compound for the synthesis of these F, G, H and I compound. In opposite to this, for multi-component reaction there is convergent reaction. In case of convergent reaction there is involvement of two or three reactants into one product, into one pot. Here you can see the addition of P, Q and R into one pot, and we get the final product of PQR. This is also a technique used for the synthesis of a large number of compounds, but here the large number is get by the variation in the structure of the P moiety, Q moiety or R moiety, and we get the products, we get single product PQR, but when we change the different chains present in P, Q and R, we get different types of molecules here. Second point about multi-step reaction, it is involve a lot of steps, that is one step after another. Here you can see A and B and mixed in one pot, and we get the AB product. It is separated, purified, and then we add C, to get the A, B and C product. But in case of multi-component reaction, it is one step, one pot reaction, that is P, Q and R all are combined in one reactant, one pot, and we get the final product. Third point about multi-step reaction is low efficiency. Due to involvement of a large number of steps, there will be a decrease in the yield, there will be a decrease in the efficiency of the reaction, and as you know, efficiency of a reaction is directly related to the percentage yield of a reaction. But in case of one pot synthesis, due to single step and one pot reaction, then we will be with the product which has too much high percentage yield, and so the reaction is termed as higher efficient. Last point is the low diversity per step, and multi-component reaction have high diversity per step. Low diversity mean after combining A and B you get C and D. Two reactants are mixed and we get two products only. In case of C, one reactant we get two products. In case of D, one reactant we get two products. But in case of multi-component reaction, there is high diversity. High diversity mean by changing the structural features of P, Q and R, as we have discussed in the last point. By changing the different structural variations of P, Q and R, we can get a large number of molecules in one step. So therefore it is said that I can explain in some other way that we have combining a aldehyde and amine in multi-step reaction. The first step is about the interaction of aldehyde and amine, and we get the product. We can change the structure of the amine. Let's suppose we have 10 amines and we have 10 aldehydes, so we can let's suppose by different combination of these we can get 100 molecules, for example, in this step. But in multi-component reaction in which we are involving amine and aldehyde, that is 100 compounds, we have already attained the 100 different varieties. But then we are adding a third moiety which has also 10 different structural features, and so this 100 will be multiplied according to this 10. So there will be a large number of products which will be attained through multi-component reaction as compared to that of multi-step reaction, because in one step only two reagents or one reagent is involved, and we cannot get a large number of variety of molecules from this construction. Here we talk about our main lecture, that is Ugi reaction. It was first reported in 1959 by Ugi, and that combination of isocyanides in undergo a 4-component reaction in the presence of amine, aldehydes or ketones, and carboxylic acids, and we get a single condensation product of these 4 components. And today this transformation is now known as Ugi 4-component reaction, U4CR. Here you can see the general overall reaction of this Ugi reaction, that a carboxylic acid bearing R1 moiety, then amine R2 moiety, then ketone or aldehyde bearing R3,4, and then isocyanide bearing R5 moiety, combined with the removal of a single water molecule, we get the final product. This is basically amide, and here you can see the different color combination will tell you about the different parts of this molecule. Here you can see the R1 and carbonyl, that is a acyl moiety which is combined with amine. Acyl moiety is has come from the carboxylic acid functionality. Then the R2N amine moiety is present here, and here you can see there is formation of 2 carbon nitrogen bond of this amine. Nitrogen of this amine is bonded with acyl group which has come from carboxylic acid, and also with the carbon of aldehyde or ketone functionality. So these 2 carbon nitrogen bonds are newly formed bonds. Therefore this reaction is kept under the heading of carbon nitrogen bond formation. Then the third at third position is the carbon in green color, which is from aldehyde or ketone moiety, and then there is the carbon nitrogen and R5 group from the isocyanide moiety. So combination of these also termed as we named it as this first R5 NH and carbonyl is termed as carboxamide, and this carbon bearing R3 R4 is termed as alpha carbon of this carboxamide moiety. And then nitrogen amine, and next is the acyl group, so we term as alpha amine. This aldehyde moiety, aldehyde carbon ya ketonic carbon is termed as here alpha. So it is alpha substituted with acyl amino, alpha acyl amino carboxamide. So overall this molecule named as this. So this is the overall reaction of Ugi 4-component synthesis, in which 4 components has been combined together to form a single moiety with the removal of single water molecule. And also due to higher activity of isocyanide, and this reacting species, we do not need to use a catalyst for the propagation of this reaction. Some more important features of this UG reaction include that UG reaction is a powerful synthetic transformation where the four reaction partners are combined in one pot under mild conditions. That is, we do not have to give a higher temperature or pressure or catalyst, etc. One of the earliest and most important application of this UG four component reaction was the peptide coupling. You can say the alpha amino acid synthesis, as we have named in the last slide. Several modifications of this original transformation has been made, and therefore we have moved towards the synthesis of heterocyclic compounds by using different functionalities here. UG reaction also found a widespread application in combinatorial chemistry, as we have discussed in the case of multi-component reactions, that combinatorial chemistry is greatly enhanced by this multi-component reaction technique, and UG is one of the multi-component reaction, so it has great importance in this field, and where due to its high synthetic chemistry, the power of this reaction has been used for the combination, for the invention of a large number of molecules, which has also been used for further applications like medicinal chemistry or some other fields of the life. In addition to carboxylic acids, that is we were using for the UG reaction, number one, there was one component was amine, number two component was an aldehyde or ketone, number three component was isocyanide, and the number four component was carboxylic acid. In place of carboxylic acid, we can use some other nucleophiles also, like hydrazoic acid, cyanates, thiocyanates, carbonic acid, monoesters, salts of secondary amines, water, hydrogen sulfide, and hydrogen selenite, and all of these nucleophiles will give a large number of different moieties, and here we also get some heterocyclic moieties also. Here you can see first on your right side, first is the basic reaction. In the center you are seeing three components, that is aldehyde or ketone, second amine, and third isocyanate. These three are mixed with number one on the right side is with R5 group is solvent 0 degree C to room temperature is the working temperature of this reaction, that is carboxylic acid. On combination with carboxylic acid, we get alpha acyl amino carboxamide, which is the basic UG reaction. Under this second reaction is given with H2O, H2S or H2SE. All of these are hydrides of sixth group of the periodic table, and here we get different moieties which are termed as alpha amino carboxamides, and these carboxamides can be carbothiamide if instead of oxygen there is sulfur, and if there is selenium, then this can be named as carboselenamide. In the third reaction on this right side, you can see the use of carbon dioxide along with alcohol, and we are using this both of the combination of this was termed as carbonic acid monoester. Here you can see in the product there is the product name is alpha acyloxyamino carboxamide, and here you can see in red color there is nitrogen with R3, and with along with the attachment is of C carbon and 2 oxygen. These three are from carbon dioxide, and R5 group is from the alcohol. That is, alcohol and carbon dioxide first mix with each other to form an ester, and that is attached with the amine. On the left side, the first member which is used along with the solvent is hydrazoic acid, HN3. Heterozoic acid, and by using this as a nucleophile we get the product which is actually tetrazole derivative. That is, we are getting a heterocyclic ring with 4 nitrogens in a 5-membered ring. Tetra mean 4, A's mean nitrogen, and ol mean 5-membered ring. So it is therefore termed as tetrazole derivative. Next second on this left side is cyanates. There are 2 categories under this name, cyanates and also isocyanates. This molecule here you are seeing H and double bond C double bond O is termed as cyanate. And then this after the treatment this with this cyanate we also get heterocycling ring, that 5-membered ring, and but this is a saturated ring and also bear 2 nitrogens. This is term name as, this molecule name is hydantoenimide derivative. Hydantoenimide derivative. The third on this left side, last one, is the thiocyanate, and here you can see that if we use this we get the similar type of molecule as we get, but this is the term name as thiohydantoenimide derivative. Here you can see in the last row of this slide that the different varieties have been mentioned here. For example, here is given R1 for alkyl group and aryl group, R2 for hydrogen or alkyl group. This thing makes should be made here clear that if we are using aldehyde, that is R2 is H, then R1 can be a simple aliphatic moiety, that is alkyl, or an aromatic moiety like an aryl group. But if we are using a ketone, then both there is found some less reactivity for the molecules bearing 2 aryl groups. That is, ketone bearing 2 aryl groups at 1 and R2 position has been found less reactive for this reaction. So therefore they have termed here that R1 can be alkyl aryl, but R2 can be hydrogen or alkyl, but it cannot be aryl along with the other aryl group. R3, which is from amine, can be alkyl or aryl group, and there is no specification for it. And then R4, that is from isocyanates, is can be alkyl and aryl group. R5 for the carboxylic acid can be alkyl aryl group. And last, the different solvent used for this reaction include methanol, ethanol, trifluoroethanol, dimethyl formamide, chloroform, DCM, tetrahydrofuran, dioxane, or diethyl ether. That is, we can use polar solvents, and also we can use non-polar, and also in polar we can use polar protic solvent and also polar aprotic solvent. Reaction moves in both of the solvents. We shall discuss in mechanism that there is some variation by the use of a protic solvent and aprotic solvent, polar aprotic solvent, or by using protic solvent. There is some difference in the mechanism, but the product is same for all types of solvents. Here you know the structure of dioxane. Dioxane is the 6-membered ring, that you can say the cyclohexane 6-membered ring, but at 1 and 4th position there are 2 oxygen inside the ring. That is, it a heterocyclic bearing 2 oxygen at 1 and 4 position. So it is termed as, also termed as 1,4-dioxane or simple dioxane. This is the overall mechanism of this reaction, Ugi reaction, that this mechanism is given with the basic carboxylic acid. First, aldehyde, here is shown as aldehyde, is interacting with the amine, and we get the imine after the removal of water. This imine interacts with the carboxylic acid and is protonated by it, and after this protonation, the isocyanide acting as a nucleophile attacks on this moiety, protonated imine moiety, and then we get the an addition product of both these reactants. In the next step, another molecule of carboxylic acid or the previously byproduct of carboxylate ion can also be used here, and a pure molecule, another molecule of carboxylic acid can also be used here. Here is another molecule shown here. It interacts as a nucleophile through its carbonyl oxygen and attacks on the carbon of isocyanide moiety, and we get the final addition product with which after the cyclization, that is the amine, lone pair of amine acting as a nucleophile attacks on the carbonyl of this acid functionality, and we get a 5-membered cyclic ring. And this 5-membered cyclic ring, after the some bond formation, that is, there is a double bond formation between carbon and oxygen, and the oxygen carbon bond is broken, which moves towards the isocyanide carbon, making their double carbon oxygen double bond, and carbon nitrogen double bond of isocyanide moiety has been removed into a single bond, and we get the final product after this acyl transfer from the carbon of isocyanide moiety to the nitrogen of amine, and we get the alpha acyl amino carboxamide product. This last transferring is a specific rearrangement which is also known as mum rearrangement. Here is also given the general overall mechanism of this reaction, but this reaction is going to be perceived in a protic solvent, and here you can see the reaction of amine with a ketone in the presence of H plus ion, which has been coming from a floating solvent, and we get the product in this first step in which nitrogen is with positive charge, and then after the removal of proton, addition of proton to OH, we get OH2 good leaving group, and then the removal of proton, and we get this moiety. Removal of proton is from nitrogen and addition of proton is to OH group, and then after the movement of this nitrogen lone pair towards the carbon making double bond and the removal of water, we get the imine moiety. This imine moiety is treated with the carboxylic acid and it got protonated in this way, and we get the byproduct of carboxylate ion. In the next step, the isocyanide moiety acting as a nucleophile from its carbon attacks on this carbon of imine functionality, and we get an addition product of these both isocyanide and imine. Then the carboxylate ion here is acting as a nucleophile, attacks on the carbon of isocyanide moiety and it got attached at this position, and we get a simple final product. Then there is the shifting of acyl group from the carboxylic acid towards the nitrogen of the amine through a rearrangement named as mum rearrangement, and you can see here first is the protonation of the imine nitrogen sp2 hybridized nitrogen, that is nitrogen with double bond is protonated. Then the nitrogen this amine, the single bonded nitrogen sp3 hybridized nitrogen acting as a nucleophile attacks on the carbonyl of the acid functionality, carboxylate functionality here, and we get the cyclized intermediate, and after the shifting of proton from imine the shifting of negative charge of this of alkoxide ion towards the carbon, making their carbon oxygen double bond, and then the breaking of carbon oxygen bond, and we get the carbon oxygen double bond here in the vicinity of the protonated imine functionality, and we get finally alpha acyl amino carboxamide functionality. So this mechanism has been illustrated in the presence of a polar protic solvent, or you can say yes, polar protic solvent.